Okay, question 3 on the 2019 AQA AS paper 2. So, this question is about photon energy and photon momentum. We're just going to look at the context of PET and a solar sail. So, talking about how we have positrons emitted from an unstable nucleus that does beta plus decay. So explain how the change in quark character in beta plus decay affects the number of neutrons and the number of protons in an unstable nucleus. Well, first things first, the change in quark characteristic is that an up becomes a down plus a positron. Okay, so your protons decrease and your number of neutrons increase. Okay, that should be it. That's really all there is to it. So, we look here. Positron interacts with an electron, resulting in annihilation. As a result, gamma photons are produced. The energy of each gamma photon is 0.52 mega electron volts. Calculate the momentum in Newton seconds of one of the gamma photons produced by this annihilation. Okay, so for that, the momentum is photon energy divided by the speed of light in a vacuum. So we need to have this in joules in order for it to work. So we've got 0.52 times 10 to the 6 times 1.6 times 10 to the minus 19. Okay, that's our energy in joules, and then divide by 3.00 times 10 to the 8, the speed of light. There we go. There we are. Equals approximately 0. Very, very useful calculator. Well, okay then, let's go to math and open up the regular scientific calculator. So 0.52 to the power of 6 times 1.6 to the power of minus 19 divided by 3 to the power of 8 is 2.8 times 10 to the minus 22. Okay, it seems like a very, very small number, but it should be. It's one photon, right? And one photon is incredibly small. It's a even though, we talk about how much energy gamma photons have, it's still an incredibly small amount of energy in one photon. The thing is, we have lots and lots and lots of them when they are there. So, Positron and electron meet and annihilate at position X. Shade the detector that will be triggered by this annihilation. So if P is triggered, what you remember, it's equal and opposite. I would use a ruler. I would draw a straight line from the middle of P straight through X. And then I would shade in the one directly opposite it. Okay? Equal and opposite conservation of momentum. Way it's got to be. And that's actually the answer to the next question. Explain my answer. So, okay. So again, we always have two electrons produced. They have equal and opposite momentum, and that's for the conservation of momentum. I always say, there's a lot of physics things where we make a lot of assumptions where we seem to bend the rules of physics, and there are some things that seem to break the rules of physics. It's just that they're using a different set of rules or a more general set of rules than what we use. But things that never get broken are these conservation laws. So momentum, energy, charge, those things, those are always conserved. Okay, in every nuclear reaction, every creation, every annihilation, all of it, always. So, velocity and time. Here we go. So we got a velocity time graph for the solar sail. Calculate the acceleration in meters per second squared of the solar sail. Well, we've got a velocity time graph, so let's do a gradient of a velocity time graph. Okay, pick convenient-ish points. Make sure you're so explicitly draw your triangle. Okay, explicitly draw it. Your triangle needs to cover at least half of the value on the x. Okay. Axis, otherwise you're not doing enough. So this is 1.1 and 65. This is so 76, 77, 78. Let's go 77.9. And here we are dealing with 0.31. Okay, accurate to within half a square. That's what they're looking for. Accurate to within half a square. I mean, if there are no data points, you could use the origin as well, but I'm doing it as though there were data points. So the only thing is we have hours here, and we're going to need seconds, so I'm going to convert that to seconds right away. So 1.1 minus 0.31, and multiply that by 3,600. 2,844. Okay, change in y, 77.9 minus 65. I feel really bad that I just used a calculator for that. 12.9. I bet you that sounds great. So 4.5 times 10 to the minus 3. Meters per second squared. What have I done wrong? Oh, units. Millimeters per second. So this is millimeters per second squared, because I wasn't paying attention. So 4.5 times 10 to the minus 6 meters per second squared. Oh, well, my class understands what I mean when I said get me the stamp. Okay, so the reflectance of a surface is proportional to the percentage of light incident photons that are reflected off the surface. Explain the effect of increasing the reflectance of the solar sail on the acceleration. Assume gravity has a negligible effect on the solar sail. So, if you have zero reflectance, then you're absorbing the photon, which means that the change in momentum is whatever the momentum of the photon is. If you have 100% reflectance, so perfect reflectance, you are actually going to accelerate twice as fast as if you had 0% reflection. Because what's going to happen is now the change in momentum is double because you've reversed the direction of the photon. So its change in momentum is whatever its initial momentum was to 0 back up to the negative momentum. So it's twice that. So your acceleration will increase. Okay, and this is because the change in momentum will be greater. Okay, so if there's a greater change in momentum, that means that there must be a greater force being exerted. So if there's a greater force being exerted, again, this is an equal and opposite. This is Newton's third law. It's the way that it works. If you're exerting a air quotes force on the photon is exerting a force on the sail. So therefore, it's going to have a higher acceleration. So if it's a perfect mirror, you get the maximum amount of acceleration. If it's a black body, you will get the smallest amount of acceleration because you're just absorbing the photons. Yeah, so that's question 3 for you.